Hi, I'm Simon Murray, Principal Engineer with Couchbase and also the Technical Lead on the Couchbase Autonomous Operator project. This presentation today we're going to be looking at the design and architecture of the operator. We're going to start at the high level with Kubernetes, what it's designed to do, and where operators kind of fit into that whole picture. Then we're going to look at the actual operator's design and architecture, drilling down a little bit deeper. We're going to be looking at networking options, how to support the product, which is very important to you as the customer, and also we're having a bit of a preview with Operator 2.1, which will be out very, very shortly. So without further ado, let's get cracking. Before we start looking at operators in depth, first thing we need to do is have a look at Kubernetes and understand, where in the ecosystem those operators actually fit. And to do that, I'm going to make a cup of tea. Quintessentially British. So what I've shown you there is making a cup of tea. So basically we've gone from getting the kettle, turning it on, putting some water in a cup with a tea bag, leaving it for a bit, adding some milk, and then finally drinking the finished product. Hooray, fantastic. Now the problem with that is it takes a long time to perform. And imagine if I'm doing that 10 times a day. If making one cup of tea takes 10 minutes, then if I make 5 cups of tea, that's 50 minutes I've invested rather than doing other things. Around the world, there are hundreds of thousands of people doing exactly the same thing, or repeating it time and time again. Think how much time is being wasted on doing that and just following those instructions time and time again. Now, as a software engineer, I spend a lot of my time looking at code thinking, how can I make this better? And it's fairly simple. All you need to do is basically look for repetition, look for, where those things are repeated all the time, where we're spending all our time writing the same things over and over again. Then we can generalize that. Instead of having, 10 instances of that bit of code, suddenly we only have one. We just have a kind of generic algorithm. And then to add a new instance of it, you don't need to re-implement that algorithm anymore. You just add another entry to a table. And that has made things massively efficient. And this is what Kubernetes brings to the table. So the previous method of making that cup of tea, that is imperative, basically. It's a list of instructions, and you basically follow them one by one by one. Kubernetes does things differently. It does things in a declarative manner. And this is kind of akin to going to a coffee shop, for example. So nowadays, if I want to order a cup of tea, I will just go, "Can I have a cup of tea, please?" "Certainly, sir." So with the declarative methodology, what we've done is we've just asked for a cup of tea. We haven't specified, oh, I need this type of water, or I need this type of tea bag. In fact, you don't care, because at the end of the day, when you're making a cup of tea, all you really care about is, does it have caffeine to put me up in the morning? And second of all, does it make me nice and warm on a cold winter's day? You don't need to have all of that detail. So declarative allows you to abstract away all of that stuff. Instead of obsessing over it, and I know that coders do have this tendency of doing this, they want to know the slightest little details. By discarding all of that, by hiding it away and not actually surfacing it in the first place, then you're left in this situation whereby, give me a cup of tea, and somebody goes away and does it for you, which gives you time to do other things. So in this case, I was able to kind of play on the Xbox or read a book. In the business world, that would give me time to do other things, such as innovating, creating new, better products. I could do other things, have a life, for example, go out for a walk. And if you repeat these things, maybe 5-10 times a day, then the savings soon build up. And within an organization, if you have thousands or maybe hundreds of thousands of people doing the same thing, then the gains are astronomical. So this is entirely why we want to do declarative rather than imperative, which gives you all of those kind of little knobs to twiddle. We want to avoid that at all costs. So this next slide pretty much summarizes exactly what we've just gone through in a slightly long-winded way, of course. So what we've done is we've abstracted away all of those kind of business processes, and we've made them hyper efficient, and that allows you to save money, it saves time. And this is all driven by a process called Google SRE, and there's a book available online. And the most important thing you need to read about is eliminating toil. I mean, that's our goal at the end of the day. It's to eliminate toil. Stop doing the things that you do time and time and time again. Now, Kubernetes itself started off as a platform for deploying kind of stateless web apps, you know, things like kind of just a website or whatever. That would be in Kubernetes. The thing that makes these things perfectly suited to Kubernetes is the homogeneous. So, you know, you can add things and remove things, and it allows you to auto-scale really, really trivially based on load, for example. Because everything's homogeneous, then everything should, technically speaking, have the same CPU utilization, the same memory utilization. So if that becomes under pressure, then you can add a few more pods and things just scale up. Because Kubernetes is designed to be used with kind of these homogeneous and stateless apps, then putting a load balancer in front of it is a logical next step, because it doesn't matter which one it hits, you know, it still works. And this also makes it fault tolerant as well. So using health checks, for example, you can see, oh, well, that pod has failed now, don't bother routing traffic to it. So we've seen how Kubernetes is a really great fit for these kind of stateless, homogeneous apps. However, there has been more and more demand from the community about stateful apps. People think, well, I've got my stateless bits in Kubernetes, why can't I have the rest and use it as the de facto platform for everything? So support is coming slowly but surely, and it's improving all the time, and this is exactly where Couchbase kind of fits in. So Couchbase can actually be provisioned homogeneous, so each and every pod has the same services running on it. It also happens to have a mode of operation called multi-dimensional scaling. This is based on the realization that you know, your data service may scale, you know, at a different rate to other services such as query or indexing. And this allows you to do that. Now, it doesn't exactly apply one-to-one, you know, with the core tenet of everything being homogeneous. However, it does give you those benefits of being able to independently scale things. You could have, you know, say different services running on different classes of machines with different hardware types. This does, however, have the knock-on effect that using things like the pod autoscaler doesn't work straight out the box. Because it's not homogeneous. You know, when you tell it, you know, I've got a 5-node cluster, I want to scale it up to 7. Which service is it referring to? You know, which class of nodes are the ones that are actually under pressure that need scaling? So these are the big problems that we've got to deal with. The other important thing to know about Couchbase is it can't be load balanced, and this is one of the questions that comes up a lot from people. They want to be able to, you know, put an ingress or a load balancer straight in front of it, and it, you know, just magically works. It doesn't work that way. The clients themselves are responsible for looking at the document name and then hashing that, and then using that to look at which node to actually write to, at which point it directly accesses that node. This is called client-side sharding. So this is another problem that we have to, in the operator team, take care of. So while Couchbase can't be load balanced, the client-side sharding actually has benefits. Take, for example, a client. If it was going to write, say, documents to a node, for example, it would basically load balance it directly to a node. If that node didn't actually have the data, or, you know, wasn't the home of that data, then it would have to route that packet onto another node, at which point the data would be persisted, then the reply would go back this way, and then back up to the client again. That's 4 hops. Now, by doing the client-side sharding instead, and basically mandating that the client talks directly to the node, then the client does the write to the correct place, and then it replies straight away. So we've basically halved our network traffic. So this final slide in the section looks at controllers, and the operator is actually just a kind of a subcategory of controller. So controllers are the things that exist for things like deployments. Now, a deployment in Kubernetes, for example, is just a kind of generalization of sets of scaling sets of pods. So basically you start with a pod as your kind of your base element, then on top of that you've got a scaling set which allows you to go, instead of having just one pod, I want n, so it allows you to do that scaling. The deployment controller on top of that adds in a layer whereby it goes, this scaling set has differed from this scaling set, so what it'll do is it'll scale that one down as it scales this one up, and that actually handles things like rolling upgrades. So as we've seen, controllers basically encode a lot of kind of business and domain-specific knowledge and encapsulate them in a single binary that's kind of easy to digest. Running an application like Couchbase, you couldn't actually do using the kind of the built-ins of Kubernetes. You'd need kind of the operator to extend it and do bigger and better things with it. So operators and controllers themselves are an abstraction layer, basically. They, based on our observations of eliminating toil, we don't want to repeat ourselves. We don't want one client in one namespace creating a cluster and then have another user duplicating that effort, especially when it can all be encoded as an operator and reused. The final thing to kind of really point out here is you're going to have to trust us on this one, but please let us handle the details. So we get lots of requests about, oh, can I do this bizarre networking? Can I do this bizarre networking? Or can I do this? We've really kind of improved over the last few releases, and we've made the operator more and more flexible, easy to configure, where we think it gives kind of, it makes sense to actually extend that level of configuration. There are certain network configurations which we actually endorse. Anything beyond that is you kind of in the realms of what's going on here. So please, wherever possible, trust us. We are kind of the domain experts on these things. If you do think that we've possibly done it wrong, we're always willing to listen. But for starters, look at the documentation. See what we recommend and see if you can actually fit into that kind of model of operating. Now that we've completed our kind of introduction into controllers and where they fit in, we need to now look at how those abstractions are actually implemented and how they are acted upon by a controller, and how actually we go about actually making one of those controllers. Okay, so the core of everything is the custom resource definition. So built-in types like deployment we've already talked about, the pods and the replica sets, they all have a type which is defined within Kubernetes, and that's all hard-coded. For us to actually make an operator which operates on things like the Couchbase cluster, for example, we need to define our own types. Now, a resource in its simplest form is literally just, and the name of the resource, and that belongs to a group as well. So our current group is couchbase.com v2. That's a version within the group, and also we have our defined types such as Couchbase cluster, Couchbase bucket, ephemeral buckets, users. The list goes on. So some of the things that custom resource definition allows you to do beyond defining those names and the groups are having a specification. So once you've defined your Couchbase cluster, you want to specify things about it. So previously, where I've talked about abstracting things away, there are certain things that you're going to want to actually kind of configure, such as the cluster size. We can't just say, hey, have a 3-node cluster, that's going to be big enough for everyone. That it doesn't work that way. So we have to actually allow a little bit of customization. Another field that's included in the custom resource definition is the status. So this allows you to specify conditions. So during the life cycle of the cluster, we can actually say, is it ready to actually be used? So there's a condition called available. Once that goes to true, then your clients can actually start consuming that cluster. Likewise, there are other conditions about balancing statuses, whether or not it's upgrading or not. These are all fully documented. So by all means, have a look and use them for your own benefit. One of the most important parts of the CRD is the Json schema. So this allows us to basically define all of the attributes within that JSON blob as it's sent on the wire that are actually valid. So we can specify that a certain field is of a certain type, aka an integer or a string, and kind of bounds. You can do validation on it. So an integer could be limited to between 0 and 3, for example. You can do all of that. Strings obviously can be matched via regular expressions. One of the other cool things that a CRD can provide is printer columns. So when you're using kubectl, for example, it's useful to say, hey, give me all my clusters. Now, by default, that would just return basically the name of the clusters and how long it's been alive. With the printer columns, what we can do is we can add extra information on top of that. So we can say what version of Couchbase Server is it running, how big is it, all of these things are like instantly available for you to look at straight away with a single command. We also do the same thing with buckets, so the I/O priority and how many replicas there are. So all of this is about making it more usable for the end user. Now, when we first started the operator, this was a long time ago, and CRDs were very much kind of bleeding edge. In fact, they still are actually to a certain extent. It was only in Kubernetes 1.16, and we haven't actually got a version of the operator yet where that is the lower bound. That brings in a load of new features that we can suddenly use. So CRDs migrated from beta into full-on GA, readiness version 1. So at the moment, I've kind of hinted about versioning. When we did Operator 2.0, we used versioning in the sense that we allowed custom resources of V1 to still exist with V2, and that was purely because we needed them to be alive during the upgrade where we migrated the old version to the new version. The only problem with the versioning back in that era was that it only actually allowed a single Json schema, and that was only applied to the latest and greatest version. And basically both V1 and V2 had to actually be validated against it. Obviously, that didn't work in this case because V2 is a complete and utter, massive change to V1. So we had to do a kind of offline upgrade, which allowed us to actually pull this off. So another good thing that's coming is defaulting. I'll get onto this in a bit in more detail about how we do it at the moment, but one of the things we like to do is we like you to be able to kind of specify your Couchbase clusters using the minimal amount of configuration. So certain things like memory, if you're trying to get up and running quickly, with a default bucket, we don't want you to have to specify, 100 megabytes is the minimum. No, we can fill that in for you, and that's what defaulting does. So if you don't specify a field, we'll fill it in for you. We make some assumptions in the operator. We assume that defaulting works, at which point we kind of optimize the code, we can get rid of all of the kind of error handling. And one of the problems with the error handling is if we did it in the operator, it would disappear into a log somewhere. Whereas if we can do all that validation and defaulting up front, if the validation fails, then we can reply straight back to you. So the workflow looks like you do a kubectl create or a kubectl apply, flies into the API, it does the validation. If that fails, it replies straight back with the user saying you've got this wrong and tells you to fix something. The final cool thing about the 1.16 or the GA release of custom resource definitions is pruning. We've all done this before. Everyone makes typos. So if I typed, I don't know, buck rather than bucket, previously that would just be accepted. If something didn't exist, it would get completely ignored by Kubernetes. Nowadays, or in a later release, probably we're looking at Operator 2.2 perhaps, that will actually report back synchronously to the user that you've made a typo, and then you go back and fix it. So I've just hinted at the fact that we do defaulting at the moment, and we're using an older version of the custom resource definition specification. Now, this is all enabled by a thing called the dynamic admission controller. So what this allows us to do is we basically, when you do an API call from your client, it goes, hey, API, do something. We can actually create a hook that actually sends the JSON blobs that come from the client to a web service. In this case, the dynamic admission controller that we release has two different hooks that you can actually specify. One of them is a mutating hook. So what that allows you to do is take that JSON blob, modify it, and then return it back to the API. So that's how we apply our defaulting. So if we spot things aren't filled in, we can fill them in, and when it actually finally gets around to the operator, it won't crash, which is the most important thing. The other important thing that the dynamic admission controller does is validation. So I've already talked about Json Schema validation. That can basically check, is the type correct? Is it within range? Does it match a regular expression? Those kind of things. There are domain-specific validations that we can actually perform. So the dynamic emission controller allows this. So again, the API, once it's been mutated, will send it back to the dynamic emission controller, and that will do kind of really, really deep validation. So a Couchbase cluster, for example, that references a bunch of buckets. So we can collect all of those buckets and work out what are its memory requirements. If those memory requirements exceed what's defined for the actual cluster configuration, then we can reject it there and then. So we can do that kind of really, really deep level of validation. Another thing that is coming soon, and if anyone has actually gone through the process of upgrading from Operator 1 to Operator 2, you'll realise that we had to basically stop all the operators. We had to perform a kind of, we had a binary which allowed us to kind of update your version 1 Couchbase cluster resource and turn it into version 2. In later versions of custom resources, there's a thing called a conversion webhook. So what that allows you to do is, okay, so when you define a custom resource, there's only one version that's allowed to be stored in the database backend of Kubernetes. However, you might have older applications that understand V1 instead of V2. The conversion hook, what that does is when you request a V1, it will call out to etcd to get the resource. That might be in a V2. The API then goes, actually it's requested in V1, so what I'll do is I'll send it to my conversion hook up here. That will do the conversion, send it back, and then it finally hits the client. So hopefully, fingers crossed, when we actually, or if we need to do a version 3 CRD, then it will be a lot more seamless, and things will just work the way you expect. So we have essentially defined our type now. You can, using kubectl, create resources of that type, e.g. Couchbase cluster, send them to Kubernetes. The API will validate it. It will mutate it and add defaults, and then it will commit it to etcd. This is the point where controllers can actually start operating on them. So the Couchbase operator will basically be listening for Couchbase cluster resources as they fly by. So one of the API calls that you can actually do against Kubernetes is a watch. So what the operator will do is it will watch for resources of the Couchbase cluster type. If it sees a modification, then it knows it has to do something about it. And this is the basics of controllers, basically. They watch for changes to a resource and they act upon it. Now, the operator is slightly different in that Couchbase can kind of go out of whack as well. So if you went into the UI, you could modify, you could modify settings that went against what was requested in the original resource. So we have to check multiple kind of locations to work out whether things need actually fixing or putting back the way they should be. Obviously, this fixing and actually creating in the first place is all reconciliation. So if you created a cluster and you wanted it size 3, then we would look at reality and go, oh, okay, we've got 0 pods, we actually need 3. So it's the operator's job then to go and kind of provision all of those. Another basic thing to think about or consider when you are deploying the operator and the dynamic emission controller is security. So the operator by default is deployed in the namespace scope. Why do we do this? Because the operator needs access to secrets. The Couchbase cluster itself needs an administrator secret. Any users you define, they all need secrets. Any TLS that you define for the cluster, those are all secrets. And by running in the namespace scope, we don't get access to literally every secret on the system. This is another good point to raise, I suppose, while we're on the topic, that Couchbase, the operator, and your clusters should probably be run in their own separate namespaces. Why? Because the operator itself can't see things it shouldn't be able to see, and likewise our support tools, which I shall get onto later, they are again scoped. They will only collect things that they actually need to allow us to kind of debug issues. The dynamic emission controller is always deployed by default at the cluster level. So this means you only need one instance to be able to validate every single Couchbase cluster across every single namespace. The good thing is the dynamic emission controller, as long as you have the latest version, will be able to validate version 3, version 2, version 1 resources as they fly by. This is usually deployed at the cluster scope because it's simpler. One of the things we're constantly doing is trying to make it easier for you to deploy and actually manage. But again, we listen, and some people have different they have different demands when it comes to actually deploying these things. So coming in 2.1, we're going to allow the operator to be run at a cluster scope, and our deployment tool will actually support this. So you only need to deploy a single version of the operator, and that will basically be able to see resources in every single namespace. Now, obviously, there are security implications. However, it does make it a lot easier. You only need to deploy it once for the entire cluster in order to create Couchbase clusters in any namespace you want to. Likewise, the dynamic emission controller, that can now be deployed in a namespace, but it can only actually listen to Couchbase resources being created in that namespace. So if you are deploying the DAC as dynamic emission controller, in a namespace, you'd need one instance per namespace in which you were kind of deploying the operator. So let's dig in a little bit deeper into actual observation. So the operator doesn't just look at pods, it looks at services, it looks at persistent volume claims. I mean, the list goes on and on and on and on. And we need to kind of constantly observe them and see whether the state has changed. So, for example, take a service. So we want it in a certain state. The user has indicated their desires in a declarative way by using custom resources, and somebody might have come along and actually manually altered that service. Now it's our job to basically observe that the service has changed and then kind of go about putting it right again. Now, I've kind of hinted that yes, you should be running operators in their own namespace, away from everything else. However, there's no reason not to. You could have other services deployed in there for other things like Grafana or Prometheus. The list goes on. And what this looks like when we actually kind of poll those services is a bit of a mess. I actually have a bit of a prop here. So imagine these generic suites are services, and they kind of look a bit like this. So every time around the loop, we get everything. We get all the different colours of the rainbow here. Now, imagine I'm Ozzy Osbourne and I want a brandy glass of only brown sweets. Then those are the ones that belong to the operator. So in that situation, now we only care about the brown M&Ms. There you go. There's a lot fewer of them there. So what we've done by filtering out only the things that we care about is we've reduced load on the API, the Kubernetes API, and more importantly, we've reduced load on the etcd, the database backend that stores all of these things. There have been horror stories. Now, if you listen to enough presentations, you'll see what happens when you scale up to hundreds of thousands of pods, for example, in your Kubernetes cluster. etcd does have this tendency of melting down. So reducing the load on the API is a good thing. Now, so that's filtering taken care of. We can actually, and the operator for all of the resources it does look at reduces it even further. So there's a thing called caching. So we actually, for all the resources we look at, we do caching. So how that works is we'll do an initial list of all the possible resources there are. So instead of each and every time around the loop loading these 12 resources or something, we've only got 3. And then each time we look at the cache and go, oh, we've only got 3. If and only if a resource is modified, and this is where these watchers come in, then is it updated in the cache? So we've basically reduced our initial load to just the kind of resources that actually exist, and then of course every time there's a change, there's only that single instance flying across the network. So that's another way where we kind of minimize the amount of network traffic, and obviously we play fair with Kubernetes. We don't want to be responsible for breaking your control plane and making etcd melt down. Now, if it used Couchbase, just throwing it out there, it might be better. Anyway, cheers. The other thing which I've alluded to is actually being able to look at and observe Couchbase and actually see has anybody kind of changed the configuration values in the UI. And we do this using only the kind of admin port. So in Couchbase parlance, this is NS server we talk to over port 8091 or 18091 if we're using encryption. Basically, we want to keep it simple, stupid, and this is it. If you ever work on my team, you'll probably hear me repeat this about 5 times a week. But at the end of the day, we don't want things to get too complicated. I mean, consider dad dancing. and then compare that to ballet dancing. Dad dancing is robust, okay, there's nothing going to go wrong with it. Whereas if you look at ballet dancing, for example, it's a bit more brittle. It looks prettier and it does a few more things. However, you know, when it fails, it's going to fail hard. So this is kind of one of the perks of my job. I have to basically moderate requests from users. Now, some of them are good, and some of them are kind of they go against this keep it simple, stupid mantra. Likewise, kind of things coming in from our product management as well. You know, they're in the same boat. And again, you know, us engineers, as I've already kind of talked about, we do have this tendency of getting a little bit deeper than we'd want to. So it's all about moderation. You know, when we're doing the operator, we need to think about making it resilient and fault tolerant. So, you know, avoiding all the bells and whistles is, you know, it's all part and parcel of my job. One of the things to realise about cloud is all of the networking stuff's a bit flaky. We don't expect things to be super highly available. We don't expect them to work forever and ever and ever and ever. So you know, there are transient errors. So to help out, you know, certain things that we do while talking to the APIs, the Couchbase APIs, I'll do retries. So certain calls, like when we just brought up a pod, for example, there's a delay between Kubernetes bringing the DNS entry up that we require to talk to it, at which point we need to do retries, so we kind of embed that in our API layer. Another thing I've kind of hinted at is if you specify TLS for the cluster, the operator will always talk over TLS, so we aren't leaking any admin passwords or anything like that over the wire. So as regards observation, here's a very simple slide. In the center is the operator. This is the thing that's kind of observing all of these artifacts as they kind of fly around the system. One of the core things we look at are pods, obviously represented here by the Docker whale, and if you didn't know already, a pod is a group of whales, and that's where that comes from. So the pods themselves, they contain metadata about themselves, you know, what server class they belong to, what version of Couchbase was it running, various bits and bobs like that. That's also replicated in persistent volumes, and one of the good things about this is if the pod dies or is deleted by someone, then we can look at a persistent volume that was backing that pod and actually extract all the metadata out that we need to actually recreate that pod. The other little chap on the left is obviously Couchbase Server. There are some interesting kind of race conditions that we discovered in the early days. So, I mean, if you looked purely at Kubernetes, you could see like pod 0, 1, 2. However, because someone's deleted pod 4, and if you try to recreate it, there could be problems with that. Because Couchbase Server still knows about pod 4, and if you try and add a pod 4 into it, it'll go, oh, hold on, I already know about you. So we need to be aware of both Kubernetes and the Couchbase side and actually kind of build up a single kind of overall picture of the system. And here is that overall picture. So we have the core concept of a cluster within the operator. So the operator is an application. It has objects called clusters, and these are the clusters that it is managing. Within those clusters, they have a set of members, and those are built up through observations. And these are the kind of cornerstone of how the operator actually works. Now, the pod is the ultimate source of truth. You know, that tells you, as I just said, what version it's running, what server class it is, so that defines which services are running. If the pod doesn't exist, then we look at persistent volumes. Again, these contain all the exactly the same metadata, so we're able to kind of know what's missing and how to fix it. And last but not least, we have our observations based on Couchbase Server and the Couchbase nodes that we can pull off the API. These obviously don't define any kind of metadata that we can use, so they're kind of they're there as placeholders to say, well, we need to get rid of this. We can't do anything about it. You know, we don't know what server class it used to be. We don't know what version it used to be. We don't know anything about it. So and in that instance, you know, the pod doesn't exist, the PVC doesn't exist. So what are you going to do? And you know, beyond delete it as it is. So that's how we build up that internal model. So once we have our data model, so we've got a cluster and that has a bunch of members associated with it, then we need to define how we're going to operate on that model. And the core of everything is the operator run loop. So I've depicted it here as kind of the holding pattern of an airport. So everyone's probably been part of this. You've tried to land, and then there's not a landing slot, so you basically just sit there spinning in a circle for half an hour and burning off fuel, etc. So this is pretty accurate. This is how the run loop looks, or it used to look, in the operator 2.0. So basically we have an approach vector. This used to be a case of it would be conditional. So the approach vector in this case would be, I've just started, I'm doing some stuff. In this case, it would be bringing up services. It will be bringing up the initial node in the cluster before it actually enters the run loop, where it goes, am I the right size? Are the settings correct? The problem with this is the approach vector had some code that did things like bringing up services, and we also have to reconcile them in the main run loop anyway, because we don't want them changing. Because if your main service disappears, then you'd lose DNS and wouldn't be able to talk to anything, and that's code duplication, and that's not keeping it simple, stupid. That's not what we want. So what if we move that from the approach vector into the actual run loop itself? The other problem is the approach vector had state. So anyone who's actually used the operator in the past will kind of dread the occasion when you restart the operator and it goes, oh, sorry, that cluster's failed. That's because it kept state lying around. So typically what would happen is we basically enter our approach vector, go, are you running? Yes. Then skip ahead and go into the run loop. If not, then do some initialization stuff. And if that ever went wrong for whatever reason, then it would go into the failed state, and it would stay failed. But we kind of, again, trying to keep it simple. We thought it was a good idea, instead of having that initial the approach vector at all, to actually put the creation code into the run loop. And this has a nice little property that it will never go into failed state again. So if it fails to create its initial pod, it will keep on retrying indefinitely, and if it's a transient error, then there's a kind of good chance that your cluster will suddenly come up eventually. The other plus point is, we've seen this many times, is that if you close your laptop and put everything to sleep and then opens it again, then all the pods would be in this kind of error state and we wouldn't do anything about it. Now, because of everything being in the run loop and it being run every single time, then we can recreate the cluster each and every time around. So if that cluster disappears entirely, we can just go, well, there's nothing we can do about it. It's probably better running than not running. This actually opens up the door to kind of a new feature that we have coming in 2.1, which is ephemeral clusters. Use these at your own peril. The problem is, when you're running kind of ephemeral pods, is that Couchbase logs are no longer there. We don't actually have any log streaming yet. That will be coming in a later release, I can promise you that. But the most important thing is you can actually use an ephemeral cluster in memory that doesn't have any persistent backing, and if it dies at 3 o'clock in the morning, it'll come back alive again. So it should mostly just work, as far as we're concerned, and that's perfect for kind of caching situations where you don't mind your data disappearing. So we understand that the core of the system is basically sitting in a loop, spinning round and round and round, observing things and putting things back the way they are. Now, for most things, for most resource types, such as services, for example, how do we do that? It's very simple. It's read, modify, write, ostensibly, and I'll get onto that in a minute. We only also update the resource in Kubernetes or via the Kubernetes API if that resource has actually changed. Again, we're playing it nice. We're not overloading the database there with constant updates. Pods themselves, however, present a little bit of a challenge because they are immutable. So if you've ever tried, editing a pod on a live system, it'll go, no, sorry, you can't do this. This is immutable. Just think of it this way: if you wanted to add some environment variables to a running process or a running Docker container, then you'd be hard pressed to do that, because you'd have to kill the container, and that would cause service disruption. And that's kind of why Kubernetes doesn't actually allow that in the first place. So this forces us into doing a kind of rolling upgrade model. So what we do when we spot that. When we first created the pod, we had this idealized form of what it should look like. When we look at the pod now and try recreating it, well, does that differ? If it does differ, then we need to take some action about this, and we need to initiate an upgrade cycle. So what this does is it goes through the list of pods that are in a state that aren't, the one that we want, and then we identify a candidate. And then what we do is we add a new pod that fulfills the kind of requirements from the specification, and then we do a rebalance of our data, at which point we can delete the old pod. And then we've kind of got a cluster where we've got, for example, 2 pods in the old state and 1 in the new state. Next time round, we do the same thing again. We've got 2 pods in the new state and then 1 pod in the old state. And then final time around, then we've got 3 pods in the correct state, and the upgrade has completed. Now, the problem with this is that a rebalance isn't a trivial operation. You've got to basically take data from one node and then shuffle it across the network onto the new node. And you're doing that n times at the end of the day, and that could take a very, very long time. Again, this is the kind of suggestion that we've seen a lot from the field. So what we've done in 2.1 is we've allowed you to specify policies that dictate how these upgrades happen. And what we have in 2.1 is bulk upgrades. So instead of doing the upgrades one at a time, well, we have this list of candidates. So why don't we just go, I've got 3 in the old state, let's create 3 in the new state, do a single rebalance, and then delete the 3 in the old state, and then you've only got a single rebalance to think about. So it gets over and done with quicker. Obviously, there is an associated risk with doing it all at once. So there's a trade-off between the time taken and how much you value your data. So be cautious about that one. Another point I want to touch upon before continuing is resource templates. So when I have talked in the past about kind of abstracting things away, so we typically add in, if somebody requested the ability to add labels to a service, then we'd add that into our custom resource in a backwards compatible way. And then the next release would come around and somebody would want annotations, and it'd be a never-ending cycle, and it would take forever to actually kind of get all these fixes out the door. So what we've done now, as of 2.1, is basically have everything templated. So whenever you specify a pod, you just give it a pod template that features all of the metadata, so labels and annotations, and anything else that's configurable about the pod itself, we allow you to mess around with. If we have kind of exclusive access to certain fields, we'll tell you about it in the documentation, and we will overwrite whatever you put in there, so that's pretty much safe. But by doing this model, suddenly you can do anything, and we can be a bit more agile. Can you do this? Well, yes, we can now, because you can just basically modify the template rather than having to wait for us to implement a feature to allow you to twiddle those knobs. Now, one of the problems is this does kind of lead to things getting a little bit more, shall we say, complicated from a configuration side. So in the future, I could envisage that we'll allow these templates still. That's ultimate flexibility. That makes us a lot more agile. It makes you a lot more agile. If you want a new feature, you don't have to wait for it. It's already there. But at the end of the day, it's not exactly easy to use. So well, we'll touch on networking in a bit. But if you wanted to, for example, do public networking. Networking over the public internet, then there's a lot of kind of disparate knobs you have to twiddle. So what would be nice to do is possibly, and obviously your feedback on this is more than welcome. We should have like a top level, what type of networking do you want? And then these are the fields that you definitely need to fill in to actually kind of fulfill that. So I hinted that reconciling things like services was a simple read, modify, write. Well, it's never quite that simple. So let's have a little delve into the inner workings of how this is achieved. Now, within an object, within a resource or whatever, within a specification, you have a set of fields, and this is what I'm depicting in this slide here. So initially, and you'll get used to this buddy terminology as we go through. Initially, basically, there are no fields filled in because the resource doesn't actually exist. So what we do is we modify that resource or template or whatever with things that have been derived from the actual Couchbase cluster resource specification. So things such as what kind of port mode is it in? The different ports, we fill those in, for example, and then we write it out to the Kubernetes API. Now, second time round the loop, and I'm introducing a new variable into this. When we read, basically, we basically see a bunch of chipmunks instead of bunnies. So the two bunnies that we actually originally wrote out, now they're now chipmunks, because we've got nothing to say that we actually set them in the first place. Also, what you can see in the top right hand corner is there's another chipmunk. So a good example of this is when you create a pod, Kubernetes will actually fill in certain fields for you, again using its own admission controller, such things as IP addresses. So those can't be known ahead of time. They are only filled in, once the Kubernetes controller has kicked in and done something about it. So in this case, irrespective of us not knowing, whether or not this chipmunk was a bunny to start off with, we overwrite it because it's in our power to overwrite any field we want to. That's our job, and the state is exactly as we'd expect it to be. Those two bunnies are exactly as they have been requested in the declarative specification, and we've also preserved that chipmunk that Kubernetes has added, and we can basically go around in this loop ad infinitum, not a problem. The problems exist when we start actually removing fields. So on this occasion, it's exactly the same as the previous slide. The only difference is that in your Couchbase cluster specification, you've removed something. So say you had a field called foo defined, and you now set it to 0. So there's nothing there. There's nothing. The pointer's not pointing to anything. We're not going to do anything about it. So when we come to the modify stage, then we've got all these 3 chipmunks. We're going to overwrite the first one with our bunny. The second one, unfortunately, is no longer defined, so we don't do anything about it. And it leaves that chipmunk in place. So when you have tried to unset a field, it's still in fact set, because we're not doing anything clever under the hood. So when you write it out, then you're still getting the bunny and the 2 chipmunks. Nothing has actually changed. So what we do now is actually start tracking the resources as we create them. So like I've discussed with pods, we create an idealized form. So when we're making a service, we say, right, I've set these fields within it. This allows us to actually spot next time around, and these idealized forms are actually annotated on the resource itself. So when we load up the resource, we can actually go, okay, this is what it looked like when I first created it, and this is what it looks like now, and we can take those 2 kind of views of the system and then diff them. Now, the most important thing is here, when we spot that something was defined previously and isn't defined now, then we can clear it out. So at this point, our overturned bunny, which isn't dead, don't worry, I haven't harmed anything in the making of this. That can now be removed by the operator, because we've actually got that view, that tracking of what was set previously. And when you start using things like Kubernetes 1.18, this is not a problem we've stumbled upon by chance. You'll notice that resources made by kubectl, they all kind of have these different fields now associated with them, so they know what's been set explicitly by the user and what's been implicitly filled in by the system. Now, tracking's all well and good, but things get a bit more complicated when you think about real-life resources. It's not just a single flat object with a bunch of fields in it. No, you could have nested objects, and this is where things get kind of a little bit confusing. So if you had a required field in one sub-object and you remove that field and you left that object still there, then things would fail, because that object required a field and you just delete the field but the object's still there. So what you need to do is kind of traverse up the tree and remove that object as well, at which point it's valid. Now, one of the things we stumbled upon was certain of these objects are kind of shared, so we can't just go around willy-nilly deleting objects when there's here's an example anyway. So this came about from us setting fields in I think it was the metadata annotations. So what we'd spotted was, well, we used to have this annotation set, so let's delete it because it's not there anymore. And then when we were looking at the diff between the 2 views, we realized, well, the annotations map isn't required anymore, so let's delete that as well. However, as you can see in the diagram over here, there was a chipmunk there as well. So some other third party had set some stuff in those annotations, and we just gone and deleted the annotations completely. So as we're pruning these nested objects, what we also need to do is look at, are there any fields still set in that object before we actually kind of take action and delete it. Anyway, once that's all done, then everything works fine, and we're good. We can now kind of reconcile resources. We can observe states. We can build models of what Kubernetes sees and what Couchbase sees, and make a kind of unified view of the world. And everything's looking good, right? Right, so there's more to life than just creating and reconciling these objects, bringing them back into what you want it to look like. There are bigger things that the operator can do, and this slide kind of summarizes that. So one of the most critical things is being able to scale your cluster. So what you first provision your cluster as, maybe say 3 nodes, that is no longer the correct size. So imagine Christmas happens and you suddenly need 6 nodes, then you can suddenly scale up. So the operator facilitates this by allowing you to add extra pods. It balances them into the cluster. Scaling down as well is important, because if after Christmas you've still got 6 nodes and you only need 3, you can get rid of them all and save some money. DR is another thing. This is a kind of this is a selling point for the operator. So if a pod disappears, and we've kind of touched on this already, then you can go, oh, actually, I'll replace it and scale it back up again. So instead of it groaning under the weight of going, oh, I used to have 3 nodes and I've only got 2 and I can't handle my workload, it'll scale it back up again so it can actually handle it. So this is kind of applicable to ephemeral clusters, which we've touched on in 2.1. So there are situations where Couchbase won't automatically fail over, and the operator will play it safe by default. Okay, it will only take action when Couchbase says it's okay to do so. Now, if you had in-memory cache that you don't mind data being lost, and at 3 o'clock in the morning, as per usual, you have a 5-node cluster and you've lost 3 of them for some bizarre reason, then Couchbase will probably refuse to fail over because there aren't enough replicas of that data. But you don't care about the data being lost, so we've got a new mode in 2.1 which is forced failover. Now, what this allows you to do is wait. We see the pods going down, okay, and then there's an internal timer that we kind of keep going, and we can use this to kind of bring pods back alive if they're based on persistent volumes. And we're also using this now for forced failover. So if an ephemeral in-memory cluster goes down, or some pods go down, and Couchbase is incapable of actually failing them over, what we can then do is actually just give it a poke and say, right, fail them over. At which point those pods are completely ejected out of the cluster, and the operator can go, oh, I tell you what, the cluster, our 5-node cluster is now 2 nodes, it needs to be 5. Add some more pods in, scale it up, and away you go. Which is pretty cool, because the last thing you want 3 o'clock in the morning is running around having to kind of reprovision clusters. What we want to do is have that cluster reprovisioned, brought back alive before you've even got out of bed, which is the most important thing. Another thing to be wary of when we are dealing with topology changes is that the Kubernetes itself can actually change. So I think in the previous year there have been 4 releases, 4 no less, of Kubernetes. I think 1.16 is going out of support in October. So keeping on top of these things is very important. You can't expect to use a version from 2 years ago and be supported. It's just not going to happen. It's completely unrealistic. So Kubernetes supports rolling upgrades of itself. So what it does is it picks a node and then it goes, right, I'm going to evacuate all the pods off that. If there's a Couchbase pod, then the operator will go, oh, okay, there's a pod down. I'll wait for it to fail over. In the meantime, Kubernetes is upgrading that node and it'll bring it back online. Now, there's no constraints there, so Kubernetes can come around to another node, kill that off, and it might have another Couchbase pod on it from the same cluster. The danger there is that if you lose too many pods, then you might have lost all replicas of your data, and that's not a good state to be in because that's data loss. So the operator constrains the number of pods that are allowed to go down at any one point. We can control this Kubernetes upgrade cycle to a certain extent, and we use pod disruption budgets to do that. So it's basically n-1. So if you have a 5-node cluster, we'll tell Kubernetes we expect at least 4 to be running at all the time, at one time. So provided you have one replica of your data, it's still there. That's the most important thing. Readiness, and this comes up quite a lot. Readiness it's used to drive the pod disruption mechanism. Typically, most people go, ready means, oh, the service is running. But for us, we actually make ready mean the data is rebalanced. And we are capable of being able to tolerate a node eviction. Which has caused a bit of confusion in the past. So people see their pods as not ready and they're like, oh, what's going on? Actually, in reality, something's just stopping it being able to actually set those flags. Something else has gone wrong in the process. So prior to 2.1, we've been doing this using pod execs. So what we do is we kind of exec onto that pod, touch a file, and the Kubernetes readiness probe could actually go, it could exec something on that pod and say, is that file there? Yes, then it's ready. In 2.1, we've actually changed that because 1.14 is our kind of Kubernetes baseline. That allows us to use readiness gates. So this is much less intrusive. We don't need to have pods exec. So people in regulated industries will be obviously having a bit of a celebration. So now all we need to do is basically do a read, modify, write of the pod resource and just add a condition in, and that condition is referred to by readiness gate. So that's all sorted. Now to section 3, everyone's favourite subject, and that's networking. So back in section 1, when I was talking about how Kubernetes came about and what it's designed to do, you should have probably got this inkling that Kubernetes is very, very good at exposing web services onto the public internet. Anything else is pretty poor at, which is it's kind of a drag, especially when your Couchbase and your network requirements are something other than just a load balancer. So one thing I'd like to impress upon you is the fact that DNS is king in Kubernetes land. That's because IP addresses are unstable, and you should not be using IP addresses ever. So we used to have a network model where we would advocate using IP addresses, and no, please don't do that. So the most important thing is the instability of it. So if we had a pod which had a persistent volume claim attached to it and that pod went away, when we brought the pod back, there was absolutely no guarantee that it will have the same IP address, which is why whenever we're creating clusters in the operator, we always have to use DNS to do so. And that's why our core service exists, a headless service. It basically gives DNS to each of those Couchbase pods and endpoints. The other important thing to know about using IP addresses is because A, they're unstable, and B, you can't know them until you've actually created the pod, means you can't actually mount TLS secrets very, very easily, and it makes it basically next to impossible. So when we say DNS is king, by using DNS, DNS is stable, okay? That doesn't change. You bring a named pod back alive, it will have the same name. The IP address may have changed, but that's DNS's problem. We don't care about it. The name is stable. DNS is highly available, so when you create a service, it creates DNS entries for the various Couchbase services. Many ways it can be used. Now, one of them allows you to have a round robin, a record for each and every pod. Another way means we can actually define per port an SRV record, which is very useful because that's what all the SDKs you use nowadays for actually connecting to the cluster. Most importantly, DNS is secure because those names are known ahead of time. The IP addresses we can't know ahead of time, whereas the names we can. Then we can actually start using and defining TLS secrets and TLS certificates for actual use with the cluster. Now, we advocate the use of Wildcard Certificates because it's easiest. If we were to start allocating per pod certificates, then we'd have to start acting as a CA, and you'd have to hand over an intermediate CA certificate and private key, which isn't great. So again, keep it simple, stupid. Use those wildcards that you provide. We don't act as a CA, and everything works hunky-dory. So this is the simplest network model, and this is the one you should be using. So as I've said before, exposing things outside of Kubernetes is for web services. And in this diagram, this is the simple way we expect the operator to be used. So the operator and Couchbase cluster will be running in a namespace somewhere, and then a client within that same Kubernetes cluster, which is represented by the blue and purple box, that will connect directly to the Couchbase cluster within the same Kubernetes cluster. It makes things a lot easier. It's using the kind of built-in native Kubernetes DNS. And then those clients, those could be, a web app, for example, which is then trivially load balanceable. And because it can be load balanced via service, then it can be easily exposed outside of that Kubernetes cluster. This next network model unfortunately caters to reality. So one thing we've actually seen since I started working here, and has cropped up literally on a monthly basis for the last 3 years, is people want to run their Couchbase cluster within Kubernetes, but then have their clients elsewhere. So everything I've just said now falls apart, because that nice simple model of having the service within Kubernetes and then that being easily exposed. That goes away, because now we have to suddenly expose Couchbase's nuances across different networks. So we've hit upon this model. Given that DNS is king, then we need to actually somehow get access by that client to the Kubernetes DNS. This is fairly simple, actually. At the end of the day, you can basically you can put a proxy DNS in front of your client and say, right, anything for this domain routes to the Kubernetes DNS servers, and it'll allow you to resolve the kind of SRV records that are required to access Couchbase Server. And when you first contact Couchbase Server, it gives you a map of basically, these are the nodes that belong to my cluster. And those, because you're using the raw DNS straight out of Kubernetes, those map entries will actually be resolvable by the client, and everything just works. Some caveats for this to work. First of all, that client needs to be able to directly route to the Couchbase server pods. So in layman's terms, it needs to be pingable. Now, most, I'd say sane people, most cloud providers like Azure and GKE, for example, they do flat global networks, so you can quite happily access a pod in America from a pod in France, for example. That's not a problem. It's only when you start using overlay networks, so things like Flannel, for example, they make this very, very difficult to do. In fact, next to impossible, because there's suddenly a DNAT boundary in there that kind of upsets the balance. So that previous into Kubernetes, or it doesn't need to be into Kubernetes. It could be, the client doesn't need to be in Kubernetes, as long as it's on a directly connected private network. This next one is something we introduced about year and a half ago. This is public networking. So what we can actually do is we can expose the Couchbase pods via load balancers. Now, instead of load balancing across the entire cluster, we have a load balancer per pod, and that allows each pod to have its own uniquely addressable IP address. And we use a thing called, you can use external DNS, which is a Kubernetes incubator project, and that will allow those load balancer IP addresses to be mapped to a DNS record, which then we can poke into Couchbase Server. So when the clients read out that map, then they have the front end's address rather than the back end's address, which is private to Kubernetes. So all this requires is a DDNS server. Things like Cloudflare, Route 53, all of those are supported. You could even write your own, as proven by our good friends in Couchbase Cloud. Now, they use this technology. They've actually written their own IP address replication into DNS, so that's how all that works. One of the benefits of this, especially for kind of a dev and test environment, is that cluster is available from anywhere in the world. You don't have to be on a private network. There's no VPNs involved or anything like that. So you can access that cluster from your home. You can access it from work. You can access it from a mobile phone if you really wanted to. So that's the benefit of that model. So sometimes, and you know, the operator tries as much as it can to give you as many hooks as is humanly possible to configure your cluster. You might need to go into the UI to actually tweak a few settings that the operator doesn't support. And to do that, you know, there is the Couchbase UI, and I'm going to go through a few of the caveats as to, you know, how we support that with the operator. Now, the most important thing is that there are certain cookies which are signed by the Couchbase UI, and that's dependent on which node you actually hit. So for those cookies to be valid, you need to keep on continually hitting that same node. So in order for this to work with a kind of load balanced service in front of it, then you need to enable client session affinity. So basically, you can look at the IP address, for example, of the client and go, right, for that one, send it always to this node. Now, if you were using, for example, Amazon ELB as a front end, that doesn't actually support client affinity, so it's not generic. So trying to provide that kind of support, we can't do, and I obviously feel uncomfortable about having something that doesn't work for some subset of people. So we will always endeavour to support, you know, what's generic across the board and what will work on every single platform. Now, ingresses can be used. Now we get lots and lots of questions about this. So we define a service which addresses every single node, every single pod in the Couchbase cluster, and you can use that as a backend for an ingress. Now, we don't support ingresses directly. You know, we when you create a Couchbase cluster resource, we don't create ingresses for you. Again, this is purely down to the fact that ingress controllers are not generic. You know, if I wanted to do full end-to-end TLS encryption, for example, how you configure your Nginx proxy and how you configure another proxy, for example, they're completely different, and they use completely proprietary annotations to do so. And by introducing vendor-specific stuff into the operator, it makes it hard to actually support all these things, because once you add one, then you have to add another and another and another, and we get into that situation where we're kind of constantly trying to keep up with the latest and greatest technology. So because that's not generic, then we don't actually support we don't support built-in ingresses. So the most generic thing that we can suggest is just using port forwarding. I mean, it's not hard. You just do kubectl port forward pod name and then 8091, and then you can hit 8091 on your local machine, and you can, you know, go from there. So that's our recommendation. That's the state of play, and so hopefully now you understand, you know, where we're coming from with that. Now, I've kind of hit upon Couchbase clients and connecting to the cluster. So when I talk about clients, I'm talking about SDKs. You know, these are the bread and butter of interacting with Couchbase. There's XDCR as well. That's basically a client. It's just a Go client that runs on one cluster and replicates data to another one. And then, of course, there are connectors that allow you to connect to Elasticsearch and Kafka, for example. And because we have to worry about all of these things, you know, we're not a little siloed team, then we want the overall experience to be exactly the same. So slowly but surely, we are through our documentation and through other kind of abstractions, we want, whenever you're defining a connection to a Couchbase cluster from any of these technologies, to be exactly the same. So slowly but surely, we're unifying it. So one of the examples I've shown you is this Couchbase cluster.namespace. That, technically speaking, should work for any kind of service you want to. Under the hood, XDCR might work a little bit differently, but because we're the operator and we stand in between those two parties, we can actually emulate the correct behavior and expose that unified experience. The other example is HTTP. We don't recommend HTTP because, you know, that can cause slowdowns on the system by using the Couchbase scheme that ensures you're using a binary protocol and things are fast. But the HTTP it's the only option you have when you're actually using those kind of public networking options. One thing to remember is all of this is enabled by DNS. Again, DNS is king. Sorry for the cat. So because it works in two ways, we can support legacy versions which understand DNS records, and they can do round robin scheduling that way. And of course, the more modern versions can use DNS SRV to look up and get the correct binary ports out. Right, moving swiftly onwards onto our next topic of conversation, which is supportability. So, having all this great technology, being able to apply it in various diverse environments is all good, and making sure it nails, that's the most important thing. But things will inevitably go wrong, and being able to support that product is probably the most important thing, because when it does go wrong, as I've already said, inevitably it'll be 3 o'clock in the morning and you want it fixed pretty quickly, because that's the last time you want to be awake. So the first thing we're going to look at is logging. So the operator itself provides logging on standard outs, like pretty much everything in Kubernetes. Like all operators, using the operator SDK, things are now emitted using the UberZap library. So what this does is it recognizes that logs are structured and they are data, and there can be tags associated or labels associated with that data, and you can use those labels to actually index things. And once you get that realization into your head that things can be, these logs can be put in a database, then you can suddenly look up things. So you can do a search and say, show me all the errors in the last 24 hours. Have those errors, increased by a kind of a marked amount. And because we're using UberZap, everything is in JSON, so it's structured that way. This is, very, very easily parsable by the main technologies such as FluentD and Logstash. So something I want to delve into here is the kind of logging levels. Now, most people don't actually really realize they exist, because every single time I see kind of logs flying past from support requests, they're always in the kind of default mode. That default mode is basically for info level things. So anything that's info or higher level warnings and errors, those are echoed out. However, we have more verbose outputs available. So at the debug level, which is debug level 1, that will start to show you kind of more hardcore things about transformations happening, in the actual core engine of the operator. It'll show you more details about what's happening at the API. So it'll show you, this call went to this Couchbase pod, with this path, and these are the HTTP codes. There is another level as well, which is level 2, which is like really, really hardcore. So if you're interested in seeing literally all the data packets that are sent between server and the operator, then you can do with this level. Unfortunately, because this is so detailed, we have full header outputs in there as well. And if you're using basic authentication, then the danger there is that you'll have your admin username and password flying around on the wire. Well, flying around in plain text in these logs. So don't use 2 in production, whatever you do, but it is there if we request it, so we can actually see the packets moving around between the various components. So the logging is there in case you need, if you want to ship it to somewhere centralized. Logging for Couchbase Server will be coming soon. You can trust me on this one. I've got a little POC working, so hopefully in the next few months that should be available. Hooray! The other important thing is using the support tool. A lot of people just kind of copy and paste the last error that came out of the operator logs and send it to someone, and that's not good enough. What we need to really see is like the first error, not the most recent one, because it was the first one that triggered the chain of events. Now, I've talked about scoping, and we do have this tool called cbopinfo. So what that will do is you basically give it a namespace and say, hey, collect everything you can about this namespace. So it'll look for Couchbase clusters within that. It will collect associated pods, services, any other resource type that we have defined. Above and beyond that, it will collect events associated with those objects, any logs that are available. The operator itself has Prometheus Metrics built in. Now, I don't expect anybody to be able to decode them apart from us, but those are all collected by this tool. And we also expose pprof ports on the operator itself, and this is very, very useful for catching things like memory leaks and kind of performance issues, because that'll especially hangs as well, because that'll tell you exactly in which routine a certain thread of operation is running in. So if something looks like it's hung, then we can look at this pprof, know exactly where it is, and we can diagnose it and get a fix out as soon as it's humanly possible. So please, 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 please use this tool. That's my only request. Now the other string to the supportability bow is it's not about supporting from my perspective. It's more about self-maintaining, and this is documentation. So we spent a long time, I literally about 2 months, end of last year, beginning of this year, rewriting the documentation from scratch. If I find too much of my time being taken up dealing with requests from sales or customers and this, that, and the other, the only conclusion I can make from that is the documentation is absolutely rubbish. So we went away, we had a think about it, consulted with all the kind of gurus and master Yodas of the documentation world, and what you see now is a massive improvement on what we used to have. So one of the realizations is that when people read documentation, they don't want to get bogged down in the details. Some people might do, so you have to cater to various people. The core concepts documentation, that's the first thing that everyone should read. It's targeted at architects. It's like these are the things that we would recommend you to do to have a reliable cluster. Using persistent volumes, how to schedule things so you don't get noisy neighbors. That's all in there, and it's done at a fairly high level, but there are links down to kind of deeper levels. Now below that we have how-to, so we kind of discussed the high-level concepts in the kind of the learning and concept zone. However, somebody's going to get told to do that, and that's why we have the how-tos, and they basically kind of have bite-sized chunks of I need to do this task, okay, this little business process. How do I do it? So the how-tos are more targeted at your engineers and how to get running fast, and they feature code snippets basically that can be copied and pasted. These are all annotated as well, so every field that's defined we kind of explain it, and again there's a deeper link into kind of the reference documentation if you want to delve deeper and actually work out how to customize these how-tos to kind of fit your particular deployment. Which brings us on nicely to the reference docs. So the resources that we've defined, our custom resources, those are all fully documented by hand. So we'll tell you about what the fields are for, how they interact, what the expected format's meant to be. Is it meant to be a string or an integer? What its limits are, etc., etc. All of the binaries that we actually give away with the operator as well. So the cpop config for actually creating your clusters and dynamic emission controllers. We could use Helm, but it seems simpler. Well, we do have Helm. We also do the cpop config binary, which allows you to very easily in 1 or 2 commands get up and running. cpop info comes with that, and there's a cpop conv tool, which is that conversion thing I talked about, going from version 1 to version 2. Last but not least, and this is probably of the most interest to people, is the tutorials. Now, certain things we'd like to document, but it doesn't make any sense. So if we started documenting how to set up GKE or AKS or whatever, well, they move at the speed of light. So no sooner have we written something than it's out of date, and that's an absolute pain to actually keep that up to date all the time. So tutorials are intended to give you a feel for how to use third-party tools. It may not work, over time. Things might go out of date, but they're there to kind of give you an idea of how things work. And certain examples of third-party integrations are how to set up your DNS when using that into Kubernetes networking, how to set up external DNS when doing public networking. There are other tutorials on fun things like Prometheus, etc. So that's also a good read if you want to look at how to integrate your Couchbase clusters into the wider ecosystem. And I think it's well worth a read to just kind of understand what you can actually do with all this technology. Wow, we've done that at a breakneck pace. Okay, so this is our final section, a little bit of a preview. I always like to embrace my inner Steve Jobs by giving the game away at the end of every presentation, much to the dismay of most of my management. So Operator 2.1 is coming soon, very, very soon actually. We've covered a lot of the kind of the improvements that we put in as we've kind of gone through, because it's easier documenting what you've been working on for the last 6 months rather than what was current years ago. So a lot of these things are kind of like what have been asked for by the community. So obviously, if you make requests on the forums, we'll pick them up, and if you annoy me enough, then things will get more and more bumped up the list. Obviously, talk to your sales people and our product managers, and they'll be quite happy to bump things up and ignore my priority system. But one of the things people have been asking for, and actually we've had an issue open for this for about 3 years now, is admin password rotation. So in 2.0 we kind of implemented a persistent store for the operator. So we try and avoid state at all costs. However, there are certain times when we still need it, and this takes the form of a config map. Well, in 2.1 that becomes a secret. Because it's a secret, you can put other secrets in that secret. One of them being the previous admin password. So the danger is, if you stop the operator and then you update the password, then Couchbase knows about one old password, and the operator only knows about the new password, which is loaded up from the secret. So when it tries to use that to talk to that, boom. So this is why we kind of cache that secret in the persistence layer for the operator until we know we've actually rotated that correctly. This has enabled full proper password rotation, proper TLS rotation, and it's pretty cool. So time marches on, and so does Couchbase. It has new features coming out. So finally, we've got round to adding durability. So this is a commonly asked for feature. So when I do a write to a bucket, because Couchbase is eventually consistent, there's no guarantee that's on disk, or even if it is on disk, that pod suddenly dies and you don't have a replica, so that data's lost. So durability adds that ability to set a default on the bucket to say, I want to make sure that before I reply to my clients that data is replicated. Another thing for you GDPR fans is expiration. So there's a max time to live. So if you commit a document to a bucket and it gets too old, then that gets automatically deleted periodically. So we can allow you to kind of set that kind of stuff now. Auto scaling, yay! I can see my friends in Europe and probably the Middle East celebrating now, the fireworks going off. So the initial cut of auto scaling is going to be cut back. Well, officially it's going to support a very limited subset of applications. However, I know for a fact that it's been architected in a clever way that it could possibly be used for anything, but that won't be supported, so take it easy. Cluster hibernation, because we can now return from the dead because of all those run loop upgrades. Hibernation is now a realistic possibility. So what we can do is say, hey, I want you to go to sleep, and it will basically kill off all the pods, and that will basically reduce your electricity bill. So if you're using something like the Kubernetes cluster autoscaler and you suddenly turn off your Couchbase cluster, then it can reclaim all that space and you can save a few quid. Last but not least, I think the most important thing is time marches on for Kubernetes as well as Couchbase Server. And pardon me, I think 1.16 is actually, at the time of filming, it's going out of support next month. So Couchbase Operator 2.1 is going to have to support 117, 118, and 119 going forward, and we have plans to be more agile when it comes to actually keeping on top of these certifications. So when a new version comes out, we'll be like that and get things certified. So we're going to be more proactive about supporting the latest and greatest Kubernetes versions. And that draws us to a close for this presentation. Thank you very much for watching. If you have any questions, please by all means talk to your kind of Couchbase sales or field people. There's also the kind of text chat that accompanies this presentation. So by all means, ask some questions and I will endeavour to get back to you. Thank you very much, and enjoy the rest of Connect.